Hello everyone. So today we're going to start on 6.4. 6.4 is going to be most likely, technically speaking, our last section in chapter 6. I think I mentioned to you before we will do 6.5, but there's no homework assignment for 6.5, and it's not going to be part of any test questions or anything until chapter 7.4. So 6.4, just like a lot of the other topic that we have, is mainly just try to take something that you learn in BC Calculus and try to expand it. So what do you learn in BC Calculus that we're going to expand this time would be basically something called optimization. So in BC Calculus, you probably remember we call that given a single variable function, single variable real value functions. Let's say y equal to f of x over some domain D. We know that it can have what we call maximum value. And yes, there are two types of maximum value that we can find. One of them is called relative maximum, and one of them is called absolute maximum. And then one of them is called relative minimum, and the other one is called absolute minimum. So hopefully you recall the differences between them. So remember, a single variable real value function actually represents a curve. So therefore, essentially, when you have this function y equal to f of x, that just basically meaning is a curve in R2. So if I draw some kind of curve in R2, now it really doesn't matter what the curve looks like. So I'm going to just basically draw something random. So I'm going to draw something like this. So that's very, I guess typical curve. So if you look at this curve right here, notice that there is this one point right here. That's kind of like the top of the mountain. And there's also a second point right here, somewhere over here, that's also the top of the mountain. And then we have some point right here that's kind of on the bottom. Okay, so these points are, generally speaking, turning points, but they have a important significance in the sense that they usually give you a highest or lowest value, at the very least around the area that's on. So these points are called turning point. They also refer to as relative maximum if it's going up to down, or if it turns from down to up is referred to as a relative minimum. And a graph like this one also shows that there is a highest value that it can achieve, and there's no other value higher than this one value. And that would indicate that at this point, the function also achieved what we call absolute maximum, because this point gives us the largest y value of the entire graph, while at the same time it also gives us the largest y value within a certain interval around it. And because of the graph continue to go down forever, we can say that this graph have no absolute minimum. Okay. So hopefully all these kind of make sense to you and you remember learning them. So what we go try to do is the following. We go try to extend. What we go try to do is we will try to extend this concept of relative maximum, relative minimum, absolute maximum, absolute minimum, which collectively we refer to as extreme values, to basically same type of function, real value functions, but with several variables. So first of all, very important to understand is how does that change the concept. So in BC Calculus, for BC Calculus, we basically have function f that map from R to R. Oops. And so therefore we talk about curve in R2. But now in 6.4, what we call about is going to be try to talk about function that map from Rn to R. So now that's different. How is that different? Because now we talk about n-dimensional surface in R n plus 1. So at the very least, some of these problems we won't be able to generate a graph to even see what it looks like. But for n equal to 2, we will still be able to actually draw the function f, because that will be a two-dimensional surface in R3. Then we should be able to see what it looks like. And we kind of would have a surface where we have the highest point and lower point. As a matter of fact, it will probably be much more accurate to define function that from R2 to R, as like having hiking and go up to the top of the mountain and go down, because as you probably realize, when you we live in a three-dimensional world. So when you go hiking, you're basically hiking on the surface of the mountain, which is basically a two-dimensional surface exists in R3. So actually it's a much closer analogy, but it's just that the math involved is a lot harder to deal with. That's the reason why you didn't learn about it in BC calculus, but now you're learning it. So before we actually can talk about how to expand this concept to function number from Rn to R, I do want to talk to you about some terminology that we need to know first. See, notice that when we talk about defining relative maximum and relative minimum, we often refer to it as that the point is the highest or lowest within an interval around the relative max and relative min. The term interval is simple to understand when it is a function, when it's a curve exists in R2. But now with us dealing with function that's in high dimension, we kind of need to do a little bit better job in defining this term and have a more important understanding as to what they are. So do want to define some terminology first. So let's talk about this term first. So a set basically refer to a collection of objects. And for us in this class, we can say that set, example will be following. A set would probably be for us, this object would most likely be vectors. So example would be something like this, R2, R3, R4, dot, dot, dot. So these are all referred to as a set. And then we can define what we call a subset. So a subset of a set is basically a portion, a part of the set. So meaning usually not the whole thing, but just a part of it. So a very simple visual to kind of see this is to think of like, here is my set. So I'm going to say this is my original set. And then we can then have a smaller collection inside that we refer to as a subset. Now, however, do pay attention to the following. Number one, a set is by definition always its own subset. And some of you might be thinking, like, wait, how is that possible? Because the word subset here, even though using the prefix of sub, sub meaning kind of smaller, but in actuality, in math definition, a subset can be equal to the original set. So therefore, a set by definition is always its own subset to begin with. Okay. Two, definitely try not to think of a subset has to have a less number of elements than the original set. A subset does not have to have smaller or less element than the original set. Even though it's part of it, and it could, and the subset doesn't have to be the whole set, but yet it doesn't necessarily have to have less elements or less objects than the original set. And once again, here is important to think about, like, how is that possible? I mean, if you just look at the picture, you can clearly see that if you think about a subset of another set, you're basically taking a smaller portion of it. So if you think about the number of elements inside as like the area, then you can see the subset should be smaller than the original set. The main reason why that doesn't have to always be true is, oh, actually I need to have an extra word here, does not have to have less elements. Okay, there you go, much better. Because you are still thinking about something that's finite. That's the problem. When you talk about infinite set, you can have a subset of an infinite set that is itself infinite, and therefore, technically speaking, kind of have similar number of elements, because we don't talk about like different level or infinity yet. And we could, and usually we describe different levels of infinity using dimensions, but that's something that's beyond what we're going to talk about in this class. Now, I know it may be hard to understand, but here's some example of it. So here's a very simple example. So imagine the following example. Imagine our original set is R3. So basically our typical XYZ space. Okay? Then we can define one possible subset will be the XY plane. Basically meaning the collection of all vectors in R3 in the form of XY0. Notice that in here, we really don't say that this subset have less element than the original set R3, because technically speaking, XY plane also have infinite number of elements as the XYZ plane, XYZ space. But we will say that the XY plane is a smaller dimension compared to the original R3 space, because XY plane, even though it exists in R3, but is itself a two-dimensional surface, and it is infinite. Now, but you could also have a finite subset. So a finite subset could be the following. So another subset could be this. Just a collection of all the vectors in R3 that are in the form of maybe A to 0, where A is between, let's say, 0 and 2. No, 0 and 3, how about that? So now, what are all these three things look like? So we can definitely try to draw it out. So here's our typical XYZ space. So we already established that the XY plane would basically be just the entire XY plane. So I can't really draw that because it's infinite. But I can draw this second subset, which is basically A to 0, where A is between 0 and 3. So technically speaking, that just simply formed this. So here's where, let's say, here's where Y is 2. And here's where A is 3. X is 3, and so this subset would just be this. Yes, you're correct. It's simply just a line segment. That part of the line Y, line Y equal to 2 on the XY plane, because Z equal to 0, so therefore it's on the XY plane, and Y equal to 2, and is a line segment that starts from X equal to 0 to X equal to 3. Or so you can think of it as the line segment that starts from 0 to 0 to 3 to 0, which is a subset of R3, and this one is not infinite. Well, technically speaking, have a finite length, but still have infinite number of points in it. Okay. Now, interesting thing is that several things I do want to also talk about is this. In order to define a subset, okay, we have to also talk about the following terminology. So let's say given a subset of actually I'm not going to define it, but I'm just going to say it's given a subset of something. Let's say this subset is defined to be something like this. So here's my subset, which exists on a larger set that we don't know what the larger set is. So maybe in this case, this subset is just basically the subset of this entire screen. In order to properly define a subset, we need to define about these two things. Number one is that this subset must define a curve. So the curve that encloses the subset is called a boundary. And then what is being enclosed, this, which is the region inside the boundary, is called the interior of the set. And of course, this is called the boundary of the set. And here it doesn't have to be a curve. It could be a curve, or it could be some kind of surface that enclose the set. Okay, so it really depends on the dimension is in. But the term I want to define would be the term boundary and interior. So boundary would be basically what go around, and then what's in between would be called the interior. Now this concept would talk even more in chapter 7, but I do want you to know the differences between these two things. The reason because I do need the terminology. To define the following two things. So now that we know the interior and boundary, I can now define the following. A closed set is a set that contains both interior and boundary of the set. So a set is closed if it basically includes a boundary, because the interior kind of like what the set is. 2. An open set is a set that contained maybe I should say that either does not contain its boundary or only contain part of its boundary. And then finally, a third word is this word is a bounded set. It's basically a set that does not kind of go off to infinity or negative infinity. Okay, so now what does it mean by include boundary, not include boundary, and things like that? So simply would be something like this. So imagine that I'm going to talk about something like, let's say something in R2 xy plane. Okay, a closed set will be something like this, where it involves the boundary and the interior. So this is a closed set. An open set could be something like this, where we use dotted line to indicate that we don't include the boundary, but then it includes everything inside. That's called an open set. And what is an unbound or bound set? Well, both of these are bound. So I can probably write that too. And both of these are also bound. So what is an unbound set? An unbound set would be something like this. Which indicate they kind of go on forever. And so this one is an unbound set. And yes, an unbound set usually would be an open set because it cannot include a boundary because it's unbound. Okay? But you could have an open set that's bound versus an open set that's unbound. Okay? Now, you might be thinking, so how does that work mathematically? So you actually learned about this already because you learned about the concept called open and closed interval. So example we're following. Note. In R1, an interval is closed. Actually, maybe I do it this way. Let's say in R1, let's say given an interval in R1. So let's say we have an interval in R1. Let's say go from A to B. Okay, so let's say here's my interval. Okay, so therefore we can actually define that A and B are basically the boundary, which in this case also referred to as the two endpoints. And while here is basically the interior. So therefore we can now define things like this. So let's say we have a closed set that will refer to something like this. That will refer to a set like an interval that's go from A to B, but including A and B. But we can also have open set, which could be AB, or AB. So all these three are open set that can have the same exact interior, but does not include all of the boundary. Now we could also have an unbound set if A is let's say negative infinity or B is positive infinity, then we will have an unbound set. So that's how the terminology works. And we just try to kind of take this concept and move it to higher dimension. Okay? So the last term I want to define before we actually move on to talk about relative maximum minimum is this word called neighborhood. So a neighborhood around a point x sub 0 is basically defined to be the following. It's basically defined simply to be a regions, to be all vector x within a regions around x sub 0. So therefore simply refer to something like this. So if you have a point x sub 0, then we can define a neighborhood around it, and that's referred to as a neighborhood. Now notice that the neighborhood, oops, okay, the H and the B kind of look the same. But anyway, the neighborhood is basically a subset that contain x sub 0 in the middle. So therefore, we could have an open neighborhood or a closed neighborhood, depending on how we want to define it. Meaning that we whether define we include a boundary or not include a boundary. Okay, and a very basic way to define a neighborhood, a very common way to define a neighborhood is to do this. Is for all vector x such that this is true, such that when you take the length of the direction vector between x sub 0 and x, and that has to be less than some value delta. And that value delta have to be that value delta have to be a finite value, so it cannot be infinite. Now, let's try to understand what this expression basically means. So when you take the difference between two position vector, you find the direction vector between them, and when you take the length of that direction vector, you are essentially forming the distance between them, and you want that distance to be less than some value delta. So essentially what you have is often referred to as a ball around x sub 0. The reason why, because this statement right here, from an R2 standpoint, you can think of it as this, as here is x sub 0, and then it will form basically a circular regions around it where the radius is defined by delta. So in this case, obviously one of the reasons why delta can't have to be finite, so that we don't want it to have a infinitely large circle, because then that would basically probably cover the entire set. So it won't be a neighborhood. So the concept of neighborhood is meaning is a local area around x sub 0. But the key is that this definition does not really define how big that local area is. It could be as big or as small as we want, depend on what we choose delta to be. And the reason why I call a ball around it, because in 2 dimensions it's a circle, but 3 dimensions would be a sphere. And the high dimension would be just a high dimension sphere. So that's the reason why I call it a ball around x sub 0. So that's probably the most common way to do it. Now, with that being said, I do want to kind of point out the following. Okay? The following. So note. So this statement right here define an open neighborhood. Okay? Where this formed a boundary, and the open neighborhood does not include a boundary, and whether it's open or closed, it still requires some kind of boundary to define the neighborhood. So even in this case does not include the boundary is still basically just inequality equal to delta. And so if I do this, if I say less than or equal to delta, then now what I have is a closed neighborhood. Okay, so important to understand what some students don't understand is that if it's open, it doesn't have a boundary. No, it still have to have a boundary. It's just that the boundary is not included into your definition of the neighborhood. Okay, because without a boundary, you can't really define a space. Okay, so now I think we're kind of ready to define what does it mean when we want to form relative maximum and relative minimum. So it basically comes from the pretty much literally the same exact definition that you have for relative maximum and relative minimum from BC calculus. So definition. Okay, let's say we're given a function f that map from R and to R. So remember, we talk about real value function, but have to be several variable. Then we can define the following 4 things. F has an absolute maximum value at vector x sub 0 if f of vector x sub 0 is greater than f of vector x for all vector x in the domain. So if you can plug this x equals 0 value into the function f and it give an output value, maybe y value, that is the highest, and no other place you can get a value higher than this one, then we have what we call absolute maximum. So, and you can probably guess what I'm going to write for absolute minimum. It just simply reverse the inequality. So f has an absolute minimum value at x sub 0 if f of x sub 0 is less than f of x for all x in the domain. So those two are actually pretty easy to define, just hard to actually find them because you have to somehow prove that the function cannot give a value bigger than whatever you have, which is actually, thing about it from a mathematical standpoint, actually not that easy to do. Now we can then define relative. So f has a relative maximum value at x sub 0 if this is true. If f of vector x sub 0 is greater than or equal to f of vector x for all vector x within some neighborhood of x sub 0. The important thing here is that it doesn't matter how big or how small the neighborhood is, as long as you can find a neighborhood where this statement is true, the function f has to have a relative maximum. And that usually gets students all confused, but the idea here is that because the number are infinite, so as long as you have a point that's higher than the round point, you basically have an infinite number of points within that area, and which is what we go define to be the neighborhood. And you can probably guess what I'm going to write for relative minimum, because I'm just going to basically write the exact same thing, except I flip the inequality, of course, just like the absolute minimum. So f has a relative minimum at x sub 0 if f of x sub 0 is less than f of x for all x value within some neighborhood of x sub 0. Right, unfortunately that's all the time I got to for today, but I think we did a lot of things here. We talk about a lot of definition of different terms. Make sure you understand review the concept of relative and absolute maximum from BC calculus, and understand the concept of what does mean by a set and a subset. And make sure you understand that a set is always its own subset, because a subset can actually be just the original set itself. And also that when you talk about infinite set, you can't really compare the number of elements inside because they're both infinite. And the terminology of open, close, and bound are all important concepts that you want to know. And of course, a neighborhood. All right. I think that's it, and I'll talk to you again in next video. Okay, bye bye.